Hello everyone. My name is Yannick Dumège from the Photo Institute, and I have the privilege of chairing this sixth webinar co-organized by the Société Française d'Optique, the GDR Onde and the DR Complex. This webinar is the second in a series of three, all of which focus on neural networks. So at the first webinar, we had two presentations that gave us an educational introduction to the main principle behind artificial intelligence and neural networks. So today we will be looking at the role of optics in the implementation of these neural networks. As always, the session will begin with an in-depth analysis of a seminal article in the field. So today we will discuss parallel photonic information processing at gigabyte per second data rates using transient states by Daniel BRUNNER, Miguel Soriano, Claudio Mirasso, and Ingo Fischer. This analysis will be presented by Muhammad-Waqar IQBAL from CentraleSupélec. We will then have the opportunity to hear from one of the article's authors, Daniel BRUNNER, from the FEMTO Institute, who will give a presentation entitled Optical Neural Networks, Computing with Lasers, with Spikes, and How to Train. And eventually, Fabrice RAINERI from the Université Côte-d'Azur and Chief Scientist Officer of the startup NcodiN will present the industrial side of things in his presentation, Photonics for Artificial Intelligence, What's Going On in the Industry. So for questions, to ensure that everything runs smoothly, you can raise your hand and wait for me to give you the floor, or ask your questions in the chat and I will relay them. So I will now stop sharing my screen. Waqar, if you want, you can share your screen, please, your presentation. Okay. And I can introduce you our first speaker. So Muhammad-Waqar IQBAL is a postdoctoral researcher at CentraleSupélec. He earned his PhD in physics from the Université de Lorraine in 2023, supported by the Lorraine Université d'Excellence ICIT program. He previously received DAED, it is a German academic exchange service, funding for his master's thesis at Technical University Dortmund. Over his career, he has received support from multiple national and international funding agencies. His research focuses on photonic hardware for artificial intelligence, with interest in neuromorphic photonics, integrated photonic circuits, optical computing, structured light, and photonic implementation of machine learning algorithms. So please, Waqar, you have the floor. You can start.
Okay, thank you, Mr. Chairman, and also thank you for giving me the opportunity to give an introduction in this webinar on role of optics and neural networks. So without wasting any time, let's start straight away. So I would like to kick off the webinar with this developmental timeline figure from the review paper of Optical Neural Networks, Progress and Challenges, published in Light Science and Applications. This figure provides a compelling overview of the field's evolution, although I would point it out that it's somewhat biased towards integration-focused milestones, reflecting the growing emphasis on compact and scalable hardware. I would just zoom in a little bit in the start. So diving in briefly, the roots trace back to the 1960s through 1980s when Lud laid the groundwork in optical signal processing. And this paved the way for key advances like in 1985, Farhat and his colleagues demonstrated the first optical implementation of a Hopfield model. And soon after, in the community, the formal definition of optical neural networks was proposed. This was by Caulfield and others, not mentioned over here. And just after that, around 1990, Dimitri Psaltis introduced nonlinearity in optical neural networks, and utilizing a photorefractive crystal, and thus enabling more complex computations via optical neural networks. Now, fast forward to the last 10 to 15 years, we have seen an explosive resurgence. Theoretical ideas have crystallized into practical on-chip ONN prototypes, blending photonics with AI for ultra-fast, energy-efficient processing that could redefine edge computing and even beyond. So actually, this snapshot shows ONNs accelerating from analog optics to reconfigurable photonic chips, chasing ultra-fast, efficient AI. Now, to build on this development timeline of optical neural networks, I would like to introduce a pivotal framework that truly bridges computation and photonics. It's the reservoir computing. So emerging in the early 2000s, it was pioneered by Herbert Jaeger with his eco-state networks in 2001 and independently by Wolfgang Maass and his colleagues through liquid state machines in 2002. These two groundbreaking models both fall under the umbrella of reservoir computing, a paradigm where a fixed random reservoir of interconnected nodes projects inputs into a rich, high-dimensional space, with only the output layer needed training. I will dive deeper into this framework shortly, but for now, know that it cracked open a world of possibilities for implementing neural networks directly on photonic hardware. Now, just a step back to answer why optics is a good option for implementing neural networks. Now, optics provide a multitude of advantages for implementing neural networks, and the first is the speed and efficiency. Now, by harnessing light for computation, photonics delivers ultra-fast processing at a fraction of the energy cost of electronics. Think of terahertz speeds without the power drain. The next is the massive parallelism. ONN could exploit the light multiple degrees of freedom, such as wavelength, polarization, and phase for parallel operations. And this could significantly boost neural network performance for complex and real-time tasks. Then, thirdly, the optics operations normally have almost minimal heat generation, which means no more thermal bottlenecks. And minimal heat means denser, scalable hardware that stays cool under pressure and perfect for next-gen AI chips. From an application perspective, optical neural networks excel in multimedia signal processing, covering audio, images, videos. And this figure on the right illustrates additional promising domains. Now, before we dive into the optical path, let's again take a quick step back to understand where this idea fits in the broader context of neural networks. So what is a neural network? Imagine teaching a computer to recognize cats and dogs in photos, not by hard coding rules, but by letting it learn through patterns, just like our brains. And that's the magic of a neural network. It's a computational model inspired by biological neurons, but it's a simplified version where interconnected nodes process data through layers to make predictions or decisions. And here is an example of a feed-forward deep neural network. At its heart or at its core, a neural network basically consists of an input layer. You can see this input layer over here, where input data, basically the images, as in this case, the images of cats and dogs. So in general, pre-processing is done on this input images to extract relevant features, which are then fed into the input layer. And then we have multiple hidden layers, where nonlinear transformations create feature representations. And finally, an output layer delivering results like cat or dog. Now, during training, the network adjusts its connection strengths or weights over here via backpropagation to minimize errors, enabling it to handle complex tasks like image recognition, language translation, or even self-driving cars. So it's efficient, scalable, and powers AI breakthroughs. Now, here I would like to give a key takeaway from this is that the neural networks are not perfect. They can be black boxes, they can struggle with temporal data, they need large data sets and are computationally expensive. But their ability to generalize from examples revolutionizes machine learning. Now, one very clever alternative to this is reservoir computing. So in the reservoir computing, the recurrent network or the reservoir is kept fixed and only the output layer is trained. This makes it much easier and faster to implement even on physical hardware. And this approach has become a foundation for many hardware implementations, including the photonic reservoir computing systems. Now that we have explored the general structure of a reservoir computing system, let's dive in a bit deeper. So the core idea of reservoir computing is to leverage a nonlinear dynamical system known as the reservoir to map input data into a high dimensional feature space. And this mapping simplifies downstream tasks like classification or prediction by embedding the data in a more expressive, feature-rich representation. So the standout benefit, the reservoir's internal connections stay fixed, no training required, as you see on this figure over here. So this is a normal architecture. You have an input layer, reservoir layer, and output layer, and all the connections from the input to the reservoir layer, they are fixed. The internal connections within the reservoir, they are fixed as well, and we only tweak the output layer bits, which are normally often via straightforward linear regression. So this approach slashes the computational demands compared to recurrent networks, which must fine-tune thousands of recurrent weights. Now, at its heart, it echoes how biological neurons handle dynamic information processing. Now, quick aside from this is that for a curious audience, there's a very related paradigm known as extreme learning machine. It's a feed-forward cousin of, let's say, reservoir computing. Here is, let's say, architecture for this. So you have one single hidden layer. You have, again, the fixed input layers, but no internal connections within. And the data strictly follows along one way. So it's also very good, blazing fast for training static tasks like image classification. Now, if we look at the physical implementations of RC, the magic is the fixed reservoir. If we say why reservoir computing maps easily to hardware, the straightaway answer is the fixed reservoir inside. So the internal connections are random and untrained and kept fixed during the training. So we are skipping the nightmare of backpropagation through time. So it's a pure efficiency for any substrate. We only tweak the readout layer via straightforward linear regression, like ridge or pseudo-inverse. And the training is done in seconds, not in epochs. Now, the best part is any physical system qualifies as a reservoir when it exhibits three essential traits: the nonlinear response for rich feature generations, highest dimensional state dynamics for separation, and fading memory that suppresses noise while retaining context. Now, if we look at the key hardware implementations for photonics, includes hybrid like optoelectronic reservoirs, which is a hybrid of light electrons. So the data is injected via lasers. Delay lines in the hardware creates recycled signals for recurrent memory. Photodetectors add nonlinearity. It's super fast, up to sub-nanoseconds for predicting chaotic time series like ML tasks. Then we have photonic reservoirs, which are pure optical setups on chips or in free space using Mach Zehnder interferometers, nonlinear media. And then there are some, as for a free space, SLM and DMDs allowed to shape light, and other phenomena like interference are used to generate the transient states. Now, there are also many other hardware implementations for reservoir computing, like analog, electronic reservoirs, spintronic, memoristic systems, and even mechanical and fluidic reservoirs. For us, we would like to focus on the implementation of a photonic reservoir computing system. So let's start with the classical reservoir computing system, which I've just discussed before. So here we have a sprawling network of interconnected nonlinear nodes forming the reservoir. Think of it as a chaotic echo chamber of dynamical system. Now, inputs are injected via spatial light modulators, spreading the signal across the network, while the outputs are captured as pixel intensities from a camera readout. Now, this is an example of a parallel architecture that allows to harvest all the transient states simultaneously, thus enabling the high bandwidth processing for tasks like pattern recognition. It's powerful, but it's demand a full array of hardware nodes. So in some sense, complex and resource heavy. Now let's turn to another clever approach, which was proposed by Apollon in 2011. It's time delay reservoir computing, or TDRC, as shown over here. Now the input is injected either directly or masked to boost nonlinearity, and it is fed into a single nonlinear component, such as a semiconductor laser. From there, the signal loops back through a delay line with a total length of tau, creating a virtual reservoir through time multiplexing. And these short time segments spaced by theta basically are the virtual, each serve as a virtual neuron, letting the system's intricate dynamics unfold sequentially. Now, this simplicity or beauty of this is that no sprawling network of nodes is required, just one laser handling the entire computation with elegant efficiency. The fading memory of required for reservoir computing is emerges naturally from this system, from the natural laser dynamics, projecting inputs into a high dimensional space for linear readout. So in conclusion, for a TDRC slashes hardware complexity while cranking up speed and efficiency, especially in photonics. So if we look at the, let's say, key advantages and trade-offs that you get while adopting this framework, the advantages are clearly the hardware efficiency, high bandwidth, easy scalability, single nonlinear element replaces network of neurons, high bandwidth semiconductor lasers enable gigahertz scale dynamics. While scalability is like number of virtual neurons could be adjustable by adjusting the delay length and sampling rate. And the main drawback comes from sequential processing, which means that a bigger reservoir would be slower. But despite these challenges, Daniel and his colleagues demonstrated a groundbreaking implementation of this scheme, where they smashed through limitations to achieve blazing fast information processing speeds, up to gigabytes per second for tasks like spoken digit recognition. And so here I would show their elegant implementation scheme, experimental implementation. So it's an elegant setup. A lone semiconductor laser serves as the nonlinear powerhouse with inputs injected either optically via Mach Zehnder modulator for intensity modulation or electronically by modulating the laser diode current. And the signal loops back through a delay line, multiplexing transient states into a virtual high dimensional reservoir. So capturing those rich dynamics of the laser for linear readout. So this setup could also be like all optical, as I mentioned, and you can also have an electronic intense modulation of the current input. I would just quickly show the performance of that setup on the chaotic time series, Santa Fe time series. So here you see basically they have, so the original trace of the chaotic Santa Fe time series is in black. The red shows the predicted. On the top, this is the original time trace for the Santa Fe time series, and on bottom you have the predicted time steps. And you see that the predicted trace of the chaotic time series stays very close to the original time trace. Now, this was the first implementation of such good photonic implementation for a reservoir computing system, and they achieved quite a bit of groundbreaking milestones in that. One of a few of them I've mentioned over here. So they achieved like a blazing fast classification up to 300,000 spoken digits processed per second on the TI-46 audio recognition benchmark. They, in terms of precision, they had a decent, reasonable error rate of around 10%, but they could handle 13 million data points per second. And in terms of energy efficiency, the system, all optical system, just used 10 millijoule per digit in fully optical versus just 2 joule on a traditional computer requirement. Okay, so now a bit on outlook. So looking ahead, the goal is to merge the best of both worlds, like photonics and electronics. So to build the powerful, efficient computing platforms. And we need continued progress in modeling, integration, and novel photonic devices that will drive up on-chip optical reservoir computing forward. And by exploring new photonic materials and ultra-fast modulators, we would move closer to realizing real-time, task-specific optical AI hardware. So I thank you for your attention, and if you have any questions, you can ask.
So thank you very much for this nice presentation. The session is now open for questions. So you can, yeah, so, okay. Ariel, you can switch on your.
I am just congratulating for this very, very clear and nice presentation.
Okay, thank you, Ariel. Do you have question? Maybe Philippe, if you can.
Yes, thank you. Thank you to both of you. Agree with the remark of Ariel, of course. Big progress has been done. It's very clear. Bravo. Yeah, I had a question about the architecture. I was believing, having understood a long time ago that when you have, let's say, like a perceptron with hidden layer, you could imagine that the hidden layer may capture some conceptual or model reduction representation of the problem. At least it was a hope initially. I don't know. And I have the impression that with this, let's say, reservoir architecture, because the connections are fixed in between the two output layers, I have the impression that maybe this representation cannot be achieved, which doesn't mean that it doesn't work. I mean, but and you gave a fantastic. What am I correct, or are my doubt? Do you understand my doubt about this? The hidden layer can, with a reprogrammable connection, may help people who are thinking. I don't know what is the status. We're thinking that they may help capturing model reduction representations, in fact. But is it possible with the reservoir architecture?
So the thing is that the reservoir computing architecture in itself it's a trade-off. So it's a trade-off in the sense of accuracy. So you keep the input weights, and let's say the reservoir weights fixed, but then your accuracy is not as high as a fully trained CNN or other, let's say, digital neural networks. So, but for most, this is like but it still captures quite a bit of information, and it's good enough for temporal or sequences. And reservoir computing has been applied across the field in all sort of machine learning tasks, and it has shown incredible performance. So this means that for some tasks, you don't need to train all those, let's say, thousands of recurrent weights. We have back propagation, which is very computationally heavy and expensive. And the thing is that this architecture favors the hardware implementation. So which is again the energy efficiency. But again, there in the next two talks, hopefully, I mean, we would definitely hear more about let's say around this reservoir computing architectures and maybe some other related schemes that are being implemented on hardware, on optics. And so in my opinion, the thing is that the community is still trying to come closer in terms of accuracy to the digital neural networks, which are like where you train all the weights, a fully trained neural network in comparison to an RC where you just train the output layer. So the thing is that the reservoir computing it's an approximation, and you are trading off it's a trade-off between accuracy and your, let's say, ease of implementation or the energy efficiency. So that's I hope I answer your question in some way.
Thank you.
Thank you. So Erwan, you can ask your question, please.
Can you hear me?
Yes, it's okay.
Okay, great. Yeah, I mean, very nice talk. Thank you very much for this introduction and review. Maybe that's a bit, a pretty broad question, but so now, we hear about these large language models, and we see how the neural networks sort of blow up in terms of numbers of parameters. I was wondering whether, like, which architecture would be the most scalable? Because right now, as you mentioned, like the longer or like the more parameters you put in, the longer the processing time in a way, since this is sequential and so on. Like just in terms of based on what you reviewed, what would be the most promising scalable platform in that direction?
So you would like to know about like large language models, like which could be, let's say, somehow on a hardware implementation, which could be, let's say, come close to a large language model, because I would say almost all of the large language models that you see, they are like digitally implemented. They require thousands of GPUs, high-end GPUs to do those, to basically even train them. Like ChatGPT 3 or 4, it required like 3 months of training, and they were using like thousands of GPUs. And if you look at the training cost, it's like 64 million euros or dollars, I would say $64 million. So it's a huge cost of training for these large language models. It has come slightly a bit down, but this is something else other than coming up more high-end GPUs, or in that sense, or GPUs which are more energy efficient. But as far as, let's say, hardware implementation is concerned, there is not much work, but in the community, let's say in optical communities, I have seen recently some papers on optical generative models. So they are coming up with hardware implementation of, let's say, generating images, image generating models. And for LLM, because the parameters, as you mentioned, they require like billions of parameters. So there are some efforts, but not like on that scale. So if you talk about hardware implementation, so there are some efforts, I would say, but I don't see an effort that big, because right now, in my opinion, we are not at that level to hardware, on a hardware level on optics. We could implement such a big large language model like a ChatGPT or some other. But on a smaller scale, like doing a small subset of, let's say, a word corpus of words or something like this is we do. So we can do, like you see, audio, images, or let's say videos, and all other stuff, like all the standard benchmarks of machine learning tasks. Yeah.
Okay, so maybe Daniel Lizot, you can ask your question, please.
Hi, hello. So thank you again for the presentation. I wanted to add on to the questions of Erwan and Philippe and kind of open something a little bit more broad. What do you think is the importance of optimizing the reservoir? Because we talk about the fact that the weights in the system are fixed and that there's a high dimensional space. And then later on, we extract as many features as we want kind of from this highly complex reservoir. And I feel like through the linear regression, we can kind of pick and choose what outputs we like the most. So it seems like there could be a lot of complexity in the reservoir that is not necessary. So what do you think is the role of optimizing the reservoir? And is this something that people are looking at?
So by optimizing the reservoir, I would say that, yeah, there is some work in the community ongoing. I would say personally, I also did some sort of, let's say, optimizing these reservoir. I mean, everyone in the community now, we do optimize the reservoir to somehow, maybe in terms of introducing a leaky rate reservoir where you control the memory somehow. And then there are lots of different implementations of reservoir on, let's say, on fiber-based, like as I was mentioning, like optoelectronics. So these are also somewhere where people look at what degrees of freedom they could have. In terms of optimizing, there are some attention mechanisms which people are again borrowing from these ChatGPT and models like this. And I've not shown it over here because this was more like introduction. But in my work, I have used some sort of attention mechanisms at the output layer to basically pick up relevant features and to allow the reservoir to have, like, in the sense that it could not handle just one task, but multiple tasks at the same time. So this is like, I would say, ongoing effort in the community. Maybe I'm pretty sure that in the next two talks, you would definitely listen a little bit more on this thing of optimizing the reservoir. So I was giving a bit of introduction, but you would definitely listen a little bit more. So this includes lots of things like attention mechanisms, some tricks and techniques to update the internal weights to somehow for the reservoir, the reservoir is dynamic, so it's no longer that fixed. But like optically to do like a back propagation or something like this, it's a little bit hard task. And I think in the community, people are still trying to find different ways to optimize, to find out different ways how we can, emulate the same effect what we have in a fully trained neural network.
I just want to specify that when I say optimize, I don't mean it in the sense of training, but I mean in the sense of optimizing the design of the reservoir. And I think in a lot of cases, we have very complex reservoirs where we don't fully understand all of the connections. And I just think it's an interesting topic, but I look forward to hearing more about that in the next talks as well.
Yeah. So just a quick, I mean, the implementation, as I mentioned, there are lots of, let's say, trade-offs between which sort of implementation you see. As I mentioned, like TDRC scheme has been enormously explored. It's like explored thousands of publications you can find on TDRC in the last 10 years or so, I would say. And people explore community they explore every architecture in all different possible ways that they could, and see where they could basically gain some advantages or let's say benefits. Yeah.
Thank you.
Okay, thank you. Thank you very much, Waqar. Maybe now we can switch to Daniel. If you can share your presentation, please.
Hello.
Okay.
Okay, all good. You can hear me. You can see the slides.
I can present you first. So Daniel BRUNNER is a CNRS researcher with the Institut FEMTO-ST. His interests include novel computing using quantum or nonlinear substrates with a focuses on photonic neural networks. He was received several university prizes and the Institute of Physics 2010 Royce Prize, the Institute of Physics Journal of Physics Photonics Emerging Leader 2021 Prize, as well as the CNRS Bronze Medal in 2022. He edited one book and 3 special issues, has presented his results more than 60 times upon invitation, has published more than 70 scientific articles, and has been awarded a prestigious ERC Consolidator grant, and is now a pilot of the French PEPR Electronique project for the France 2030 initiative. So please, Daniel, you have the floor for 40 or 45 minutes.
Thank you, Yannick. It's a great honor for me to present these results, and it's a little bit bittersweet because it also shows, or it reminds me how long I'm now working on this, and how interesting the work is, and how fulfilling, but also how tricky it is. So I was asked to provide a little bit of a contrastive talk, which is well suited to what I'm doing lately. I like to challenge a little bit more the narrative in the community. But I have a lot of slides, so maybe Yannick, can you give me a hint, like 3 minutes before I'm supposed to finish, because I will for sure have to jump some slides before coming to the conclusions.
Okay.
Okay, great. Good. So I was really interested by the questions raised before because they are almost following the outline of my talk, and in particular the training question, the cost of training, the benefit of training, and moving beyond the reservoir computing scheme is, I would say, almost at the center of my research interest in the past year. So it's exactly the questions which just came up. Good. Today, I focus on computing with lasers, with spikes, and how to train. We also do a little bit or quite a bit of work in 3D integration because I think one of the big insights in the field in the past years is that the classical integration approaches simply do not reach the size that is required to challenge, of course, GPUs, but in general to reach system sizes that become really, really relevant for applications. So I will start with some initial thoughts. I quite often in my talks use neuroscience and biology as a backdrop. That means I do not want to build neuromorphic computing systems. Neuromorphic is another one of these words that is a little bit misused, and there's some articles coming out about it in the last days. Neuromorphic means, for morphism, we do something like the brain, but I would say even a classical neural network is almost as far from the brain as it could be. It is simply connections and a nonlinearity. But I think biology can give us great inspiration, and it also can serve as a humbling example to realize how far we are actually away. So one of the most powerful plots I've ever seen is created by Kwabena Bohan from Stanford. He's a true neuromorph since decades, coming from the school of Carver-Mead, the founder of the field. And this is in combination with Susana from Sao Paulo in Brazil. She is essentially the Pope of scaling in neuroscientific biological systems. So what she has done is basically provide a map in how many neurons are within each mammal and in any biological brain. So she developed the method for this, and now we can essentially say this brain for this animal has so many neurons. At the same time, of course, we can measure or approximate the energy consumption. So we know the brain takes around 20 watts. It has, give or take, 86 billion neurons. And if we look at this plot here from Kwabena's paper, what we see is there's a really reliable linear scaling mechanism for the number of neurons versus the energy consumption of biological brain. It goes all the way from humans down towards a fly, and these systems are really remarkably close to a linear dependency. So this is what we can achieve, or what biology achieves, with sparse 3D integration networks. So, and we can now make a game. We can see how much neurons could we create in a network when we simply tip this component, this exponent of the scaling law. If we go from exponent of 1, we go to an exponent of 1.5, and we say our power budget is limited. You can't consume much more power, for example, in your cell phone. The power budget usually is your constraint, also in our CPUs and GPUs. If you now tilt this law from an exponent of 1 that we find in biology to an exponent of 1.5, then with the same 20 watts instead of 86 billion neurons, we can create a neural network with 18 million neurons only. If we now go a little bit more aggressive, and this is not very aggressive, we go from exponent of 1 to an exponent of 2, then with the same 20 watts, we can only build a neural network comprising 300,000 neurons. So this shows the power and the importance of scaling in computation, and in particular of neural networks, because that means we go from the human brain towards the brain of a mouse, towards the brain of a fly, simply by raising the exponent of 1 to 2. And the sad truth is that almost, I would say 99.9 hardware demonstrations, being it classical, digital, or neuromorphic, as it is right now, work with an exponent of 2. And this is the power penalty we are paying, and this is why all of AI right now is essentially predicted to consume 20% of the global electricity within 2045, I think. So this is the core of the challenge, and this is the task we should address. The big motivation is always given that the structure of a neural network, we see here topology, we've seen this in the great talk before also, is a densely connected system of nonlinear units. If we now transfer this into a digital computing platform, then the problem is we have this almost, long-standing and never-changing separation between transformations, operations, and memory. The problem is these systems are so big that you cannot store all the weights or all the connection strengths close to the operation. You need external memory. And the problem is that this external memory loading into the computing system requires a lot of energy, and is referred to generally as the von Neumann bottleneck. The real scale of this problem can be seen here. If we just do a floating point operation, that per se usually is a linear, or referring to linear operations, we need around 100 femtojoule. If we go communicating off the chip, i.e. to an external high-speed RAM, then we need 1 to 20 picojoule. And this is really where we burn all the energy. And ideally, many of these operations could even be implemented passively at attojoule energy costs. The general view is that we can get around of this challenge using a concept called in-memory computing. In in-memory computing, the neural network really is implemented usually as a true physical mirror image of the neural network computing concept, i.e. neurons here could, for example, be nonlinear units, but especially all of these connections are realized for example, in this electronic circuit using something that is referred to a resistive crossbar array. And then simply using the accumulation of currents when applying voltages at these inputs and using the accumulation of currents at the outputs, the resistors or their conductance represents these weights. And now you get rid of this shuffling of memory from external RAM into the processor. So that's mostly the approach that we're trying to implement. However, this is all good on paper. In reality, this becomes much, much more challenging. And I will say a few words on this specifically for optics, but also for electronics at the end. Another important backdrop for my research, again, comes from biology, and it compares two different metrics. The first is the speed of the human brain. So if we look at the atomistic units in the human brain, let's call them the neurons, we see they work on time scales on a millisecond range, give or take 10 milliseconds between a spike. And then we can compare this to the fastest reaction time, the response times humans can achieve, and these are around 250 milliseconds for identifying if a picture includes a human or another subject or another object. And apparently evolution has really made us efficient and fast for doing this. I guess it's because you want to know if there's a tiger somewhere in the, in front of you, or if this is the friend of your community, and you don't have anything to fear. So this shows that between these two, there's only maybe give or take 1 order of magnitude difference, i.e. the response times of individual units versus the response time of the full system. And we can show that this corresponds to only the propagation delay, let's say from your optic nerve towards the different processing areas within your neocortex, and then all the way down propagating the fingertip from the brain to the fingertip until the human test subject presses a button. Similar things can be said about the energy efficiency. Do not really worry too much about these graphs. What it essentially says that within the neocortex, 90% are used for spiking and signaling, and only very, very few things for any other transforms or any other processes that we do not assign to information processing. So this includes really everything: learning, keeping the system, the body alive, recycling, all of these kind of different byproducts of the reactions. So it is incredibly efficient. Now we can compare this to our current hardware. The timescale of a single transistor switching its gate is 10 picosecond or even faster. So single transistors achieve terahertz scales. So this comparison of optics versus electronics in terms of speed is very delicate, because we always need to specify we're talking about a system level, not a component level. At least as long as we don't reach femtosecond or attosecond timescales. However, the inference time of using a classical GPU, for example, for using a neural network is only 1 millisecond. So there's orders and orders and orders of discrepancy between response time of the component versus response time of the system. And exactly the same is for the energy efficiency. Switching a transistor gate, again, uses around 10 attojoule. But the energy of a floating point operation is 1 picojoule. So that means somewhere in between there, and you cannot just accumulate several transistors in order to get to a certain bit resolution. No, you have to do many, many, many other things which are not inherent to the energy efficient principal device. And this is again where we burn a lot of energy. A comparison, for example, if you just want to multiply two numbers, you can do this analog with a very simple scheme as seen here, or you can try to do this digitally, where you have many, many different gates, all with half adders, full adder, all combined. This here requires around tens to hundreds transistors. This here reaches quickly 1,000 to 10,000 transistors. And essentially this is what we are doing. So these are a little bit the two worlds that we are going back and forth from digital classical computing hardware, analog computing hardware. So finally, why is analog and all these systems we're talking about essentially analog, especially in optics? Why is analog helpful and can potentially offer something for the future? So here I want to cite some of our work for the first time. The question first is, can we actually build neural networks with analog units? So analog units are noisy. And the question is now, what happens if we have layers of numerous of these analog noisy units? and then we even cascade them from one to each other. Does all of this noise build up? Do they add constructively, destructively? Does the noise level essentially remain constant across the network? At the output, can we achieve situations where we have complete quiet or a completely noised signal? So we did some very analytical, theoretical work. So here you always see the lines. These are essentially the analytical model of our deep neural network, which is nonlinear and trained for a certain task, whereas the data points are numeric calculations. And here, just using this connection statistics between the neural network and those you can easily get from a model, as well as the noise properties of individual neurons, we can now perfectly predict for an engineer, you want a neural network with a certain signal-to-noise ratio at the output, this kind of neuron properties you need. The other big message here is we derived in this paper something we could refer to as a noise operator, and it is a bit like in error backpropagation, recursively defined. The noise in layer n, i.e. closer to the output, depends on the layer before, layer n-1. So S is the noise operator. And what you can see here for certain different parameters, and these tune the nonlinearity in our neural network, we can see that essentially all of these noise operators reach the diagonal. And as soon as they reach the diagonal, noise does not increase anymore if you make your neural network deeper. So what that means, even for bad neural networks, your noise or your signal-to-noise ratio does not collapse, or your noise at the output does not diverge. More interestingly, here, these are all for strongly nonlinear system. If we go to a neural network that per layer, and that's the importance, per layer is weakly nonlinear, actually noise can be averaged out and completely suppressed unless you have correlated noise. So if you're more interested in this justification, you can down here look at this reference. So this gives us more or less a justification. Why is it a good idea to build neural network, or why is it possible to build neural networks using analog hardware? I mean, one might say, you might not be surprised, the brain makes it work as well, but the brain is very advanced, and this is just using simple nonlinear units. So the justification to switch from digital to analog lies within this very fundamental scaling between the two concepts, where we can relate precision and energy consumption. So these are in unit of kT, so let's say the atomistic energy consumption unit. And this again is another paper by Kwabena-Bohan in 2017. We can look at here precision. Forget what neuromorphic means. Let's just compare analog, and this is digital for different technology nodes, so 19 nanometer or 28 nanometer. So you can see this already back in the past a bit. But we see that for low precision, we have orders and orders of magnitude energy advantage between an analog and a digital encoding scheme. It is only later for high precision calculations the digital takes over. And these precision values are actually quite easily achievable in our analog hardware laboratories. So it's quite okay to achieve 6 or 8-bit precision with your optical systems. 10-bit becomes a bit more struggling. And for this, we can expect 4 to 5 orders of magnitude more energy efficient encoding than if we compare this to a digital scheme. So these two slides I wanted to include because then we can really justify, because essentially this now links to my previous slide, that we show that we do not need excessive precision in neural networks because the noise is averaging out and it is always bound. It does not diverge. So this basically is the chain of argument. First of all, we do not need high precision. Noise in this case represents precision. And lower precision justifies analog computing by orders of magnitude less energy consumption. And these kind of energy scaling laws, we are not so far away. Just using a laser and a photodetector, you get within order of magnitude of these energy consumptions per bit of precision. So now I go to the autonomous computing with lasers. The system we're really, what I always say, abusing in a couple of past years is a classical optical laser, semiconductor laser structure called a VCSEL, a vertical cavity surface emitting laser. They can be everywhere. You can buy them literally for €5 from Amazon or whatever online delivery system. Why do we dare to call those a layer of a neural network? So a VCSEL has this structure. At the bottom, you have a mirror. At the top, you have a mirror, like in most lasers. And in the middle, you have an optical amplification medium. So first of all, why is this a network? If you have a small VCSEL, you have a single mode emission. that clearly is not a network, or you can say it's a three-dimensional network because you have phase, amplitude, and carrier inversion as the three variables. However, if you increase the diameter, then of course you get a multi-mode system. You get a lot of modes. And then these modes can interact because interaction mediated either by carriers or by photons. So local interaction is mediated by the carriers because inside of the quantum well here, for example, you have diffusion processes and they interact with their neighbors within a range of, let's say, give or take 10 microns. You get a global coupling because as a photon is emitted, let's say at this position within my cavity, the original size of the wave package is more or less given by the NA of the largest NA of the VCSEL. But then, so that would say a couple of micrometer in size. But then as it bounces through the resonator, during its photon lifetime, diffraction leads to spread of that wave function. And this goes to around 100 micrometer diameter within the couple of picosecond lifetime within the cavity. So that creates a global coupling. So the second ingredient we need besides coupling is the nonlinearity, and semiconductor lasers are full of them. Lasing threshold, a phase amplitude coupling similar to the carrier effect, but it's on much slower timescales and gain saturation. So this is why we dare to do this kind of analogy that a non-optimized large area multimode VCSEL is similar to a reservoir as we have seen it in the previous state. So how do we information process with these devices? Here you see the laser without any optical input, just electrically biased above threshold. Now we inject a multimode field. This could, for example, be a scenery, an image, a pedestrian walking across the camera of a car, or it's not a camera, in this case the laser, but the pedestrian walking is injected into the laser. If we do off-resonant injection, you see nothing is happening. It's just a simple two fields, the intensities are superimposed and square, and there's no real interaction. I.e., we don't have a nonlinear transformation, we do not really have a reservoir. If we now put the two on resonance, this changes drastically. We have this self-organization, we have a very sensitive behavior of the modal distribution versus the particularities of our input, and we get these kind of nonlinear Turing patterns in the laser's near field. So this corresponds to a dimensionality increase of the injected information. This is exactly the effect we then leverage for computing. So to build this system, I have purposely removed here reservoir and call it now an RNN, because we now, since a couple of years, are beyond reservoir computing in my team. We take an input information, that is the image on a DMD, for example, a handwritten digit. From there, we inject it into our recurrent neural network. It's still recurrent because, you still have these intra-layer connections within the reservoir that I just introduced, according to an injection matrix. Then we have the nonlinearity and the transformation in the reservoir or in the RNN, in the recurrent layer. Then we have our readout weights to project it onto the output. For example, for 100-digit input, if this input image is a 5, then output number 6 should have the highest intensity. How we do this in the experiment is we have an injection laser that is tuned to the wavelength of the VCSEL. Our input information is displayed on a DMD. That's just a spatial light modulator with mirrors, so it's much faster than SLM, which is why we use it for the input information. The input weights are represented by a multiplication of another spatial light modulator, phase or amplitude modulation, and we propagate our signal through a multimode fiber, which adds another random connectivity on top of it. So here, experiment versus the scheme, input information and SLM and omega in are switched in order. But since we do a pixel by pixel multiplication, the sequence doesn't really matter. It was just easy in the experiment to implement like this. The near field output here, we now image on top of the VCSEL, i.e. we inject it into our VCSEL. The reaction of this laser to the particular input image is then imaged again on another spatial light modulator, or in this case, the same spatial light modulator, which is then applying the output weights before we detect it. So this means in the system, all information processing is happening physically by wave propagation, by diffraction, by nonlinear transformation due to the laser rate equations. And there is no digital or classical pre or post processing going on any longer. There is only sending information in and getting optical power at the output. Everything is done physically. we could run this entire experiment controlled by a very simple FPGA or Raspberry Pi, and is actually something we are trying to do right now. So that's our physical system and I will use that one to explain different concepts now to train the neural network. So for example, you might reformulate it, and what I am interested in lately is data-driven programming of analog computers. Because ultimately, our neural network is an analog computer, and I do want data-driven, not premeditated programming. So for this, I like to use this comparison. On the left side, we have more or less how we humans are learning. On the right side, we see what is done currently in machine learning. So here we have a kid learning how to play tennis, and we have a teacher next to it. And there's some interesting details about how this goes about. So the teacher gives very high-level feedback to the girl learning how to play tennis, and the teacher is completely agnostic about the neuronal state of the girl, about the topology of the neural network, anything. So the teacher does not know anything about the kid playing tennis besides where the ball goes and where he said the ball should go. And the same is even true about the girl. The girl doesn't know anything about its brain activity, topology, etc. It just explores different configurations and tries to find out where did I do better, and tries to identify the systematic relation between modification and improvement in response. Deep learning is almost orthogonal to this. In deep learning, in the error backpropagation algorithm, you need to know everything, and I mean absolutely everything. The connections of the network, you need to know the activity of each neuron for each example of the input, you need to know the derivative of this, and you need to basically calculate transposes of matrices as well. So it's completely contrary, these two different ideas. So we are in my team focusing on this kind of approach where we use evolutionary and reinforcement learning strategies as well as measure gradient estimation, and both of them I will split. So the first evolutionary kind of algorithms, they all more or less follow a scheme like this. Here we see our performance landscape. Yellow means good, red means bad. And now we want to shift the system from a bad initialized point towards the optimum. How can we do this? Every blue data point here corresponds to a trial at a certain stage before we change the configuration of the network. So for example, in our laser, this would mean every blue dot here is different images put on the spatial light modulator corresponding to the weights. And then for each image, we push a couple of 100 or 1,000 examples of the handwritten digits through the system and measure the error. Then we have collected this data on the cloud, and then we create a next generation of this SLM weight cloud, for each of which we then have to push our data through the system again. So the easiest would just be you evaluate the performance of random distributions of your weights. Then you take the best result, you make this the average of your next distribution, and you repeat this and repeat this and repeat this. This is how this illustration basically goes about. But of course, there's better methods, reinforcement like policy gradients, etc., genetic algorithms. Ultimately, they all work like this. And the big advantage is they're model-free. I don't need to assume anything about my device. I wiggle my system. I try to correlate how performance behaves as I wiggle in certain directions, and then I go forward. So the first way we've implemented this is with discrete weights, where we use the DMD also at the output. So trinary weights, -1, 0, and +1. The problem is with this, you cannot really use these kind of analog wiggling schemes because it's too discrete. So we updated something called a simulated annealing algorithm. I will not go really down into the details. You can have a look at this publication from this year. We updated the simulated annealing. Essentially what happens is that here we only train the readout weights that are trinary. And at each stage of the optimization, we invert a certain number of weights. And then we see if this inversion was good or bad. If it was good, then we keep this inversion. If it was bad, we do not. And the question is now, how many of these weights do we wiggle? And this corresponds to an annealing schedule. Is basically the temperature of simulated annealing. It's basically inspired by metallurgy. And what we introduced is that the number of mirrors we are wiggling at each optimization epoch is proportional to our error. That means at the beginning we wiggle many, at the end we wiggle very few. And the cool thing is here that it improves the performance of simulated annealing a lot, and it uses dramatically the number of hyperparameters you need to scan. So here is our scheme. There is some more thermoadaptive simulated annealing scheme with many more hyperparameters, and we achieve the same performance quicker with less hyperparameters. So we've implemented this in our system, and here you can now see the performance for this MNIST classification digit task. Digital linear is, for us, I would define the gold standard as, or not the gold standard, but it's the criticality threshold. As long as we're not better than a digital system, we are not justified to introduce our energy consuming lasers. So this here, of course, is computed with computer, so it has full precision, etc., etc. But yeah, it is a little bit the threshold we place ourselves. So this is given for all the different digits in the green bar. With our trinary weights and our simulated annealing algorithm, we do start to get close. And I would like to stress again here, there is no post-processing going on whatsoever. But we never beat it. For not a single class, we surpassed the linear threshold limit. So now we replaced the trinary readout DMD with a 10-bit SLM. Ultimately, we only have 8 to 9-bit because of the 2-pi periodicity or the pi periodicity. But anyway, we now use this also to start dimensionality analysis of our laser, because the question is, how many neurons does our laser provide us? What we do for that is we first only look at the readout weights. Our input weights are not yet optimized with one of these black box optimization concepts. And then what we do is we group many pixels together to one pixel. And this is essentially the data down here. And then we train the system. And with this, we only get to around 80% classification accuracy. And then we make these superpixels smaller and smaller, i.e. we give more and more trainable dimensionality to the system, and we study the impact on performance of this. And you can see always for not optimizing the input weights, and up here is the linear limit, this dashed line, and you can see if we only train the system as a reservoir, because here we're not optimizing the internal or the input weights, we never really beat this linear limit. We had one laser that was much better than this one. Unfortunately, it died after we trained it, so we don't have so representative data for this. With that beautiful laser, we were able to surpass this linear limit, also only training the output. However, as soon as we start training the input and the internal connections, we see a big difference. So here we now clamp our output dimensionality at 2500. So this is remarkable for two things. Well, or for one thing. Our single device that has not been etched, structured in any way, it's a laser that costs you 5 euros, maybe 100 euros. It reacts at, or it can react at 20 gigahertz scale. It has up to 60-70% wall plug efficiency. It provides at a couple of milliwatt energy consumption already thousands of neurons in this case. So this is really promising, and it shows that if we use hardware a little bit more creative in this direction, we actually can really become competitive compared to digital computing paradigms. But there's many other caveats to this story. Now we start training the input, and again we do the same trick with scanning the input parameters and the parameters of input and recurrent layer training. And we see a strong increase of performance starting from this 85, 86 threshold without any input training, reaching now 91, significantly surpassing this linear threshold. Again, for our most beautiful device, we reached here 96.5% actually test accuracy for the MNIST, again without pre and post processing. And as far as I'm aware, for a fully analog system, this is the record so far ever achieved using electronic optic whatsoever. Now here a little, I'm almost begging for this. This was the work of a really outstanding PhD student, and we somehow missed the time to publish all of these beautiful results or submitted them because we're working on far advanced, more advanced things right now, or we go into a different direction. So all of this work is in this archive paper. It's almost 20 pages long because it's 2 chapters of the PhD thesis, and we will not submit this. So please, if you are interested in this, cite the archive paper. Don't wait for another higher impact publication. We will not submit this. This is where it will remain. It includes all the algorithms, etc. It's a beautiful work to read. If I may say, I'm trying to give kudos to my PhD student, previous PhD student Anna Scully here. So this is where we at. Now, in a really interesting collaboration with the team in Poland, which is creating non-circular VCSELs, we have now started to investigate the interaction of this dimensionality versus the performance of our neural network. And for the first time, we can now plot a scaling law, again on a double log scale, of the computing error versus the number of principal components. So I don't have time to go into detail here into this. We use principal component analysis as a model agnostic kind of measurement of the system's dimensionality, i.e. number of neurons to determine how big is our neural network. And we can start to see a clear carving out of the scaling law between performance and dimensionality of the neural network. So this is like the scaling law of analog computing in our systems. And I'm really happy that this work is strongly continuing. And here we are starting now, we're making first steps to link this actually to fundamental laser properties. What we plot here is the number of modes versus the wavelength of the VCSEL. And then we determine this dimensionality, the number of neurons versus the wavelength of our injection laser. So we can see a clear correlation with the local mode density, if you divide this number of modes by the integration window, between the number of modes as well as the size of the neural network we are able to realize in the system. So this will most likely be published in 2026. And what is so crucial and important about this is that this now gives us a path towards optimizing, for example, shapes of these VCSELs, do more fundamental studies. Where does this dimensionality come from? Where is the nonlinear science behind this? And essentially here we're now first time linking, first of all, the importance of these dimensions for computing. Second of all, the origin of these dimensions with the physical system standing behind it. Good. Finally, I will very quickly now, because I want to go to the training a little bit more, talk about how to compute with spikes and what excites me personally about spikes. We have created a testbed system where we have an SLM being imaged pixel by pixel onto a camera. The spatial light modulator is then driven by input information like a reservoir computing scheme. So we have input information U, random injection matrix, omega inject, some scaling component, etc., etc. We add this to a bias. On the SLM is imaged onto a camera, and this forms a loop. So this creates this kind of recurrent state equation we have here for the classical reservoir computer. Now, of course, many people have done this. We have used a system like this since 2017. Also in Metz, Damien Rontani has done really interesting work with this kind of system. And you rightfully say, this system is not excitable. This cannot create spikes. True. So what we have added to this is we have added a high-pass filtered component, i.e. a sliding window integrator that feeds back negative into that system's argument. So, and what happens here is now we can look at the stability diagram. So let's say we sit our system here at this point, choosing bias offset here. So that's the rest point of the system without any input. We now drive the system with an input here, and we see here this the fixed point of the system, stable fixed point, unstable fixed point. As soon as this drive crosses unstable fixed point here, the system gets projected towards the upper stable fixed point, and this would normally be by stability, because then the system would just do its stuff around the attraction basin of point C. And this is now where this negative low-pass feedback forcing comes in here. As long as we're down here, that term is really small, and the system is just shifted a little bit. However, as soon as we become big in amplitude, that integratory term explodes, And since it has a negative feedback, that means up here that term explodes and starts to force our system back down here. So that means without input, we rest here. The system will relax back to this point if we do not cross unstable fixed point B by the external drive, i.e. that creates the criticality you need for excitability, but then you need to be brought back to that rest point, and this we achieve by this negative feedback. So with this, we have implemented, admittedly, a very slow spiking optical neural network. However, we have 40,000 neurons, and we can now inject that with, for example, MNIST digit data. And you see these are the spike trains that are created by this optical system as a response to digit 2, 8, and 1. All good. Why do we want to do this? And this is a question always is answered very easily. Why, or people answer this very ad hoc. Why is spiking nice? People say energy efficiency, people say robustness to noise, but the details of these arguments are very, very tricky. It is very difficult to show that the spiking system is more energy efficient or more robust to noise if you cannot link it to an information encoding scheme. The power of this information encoding scheme I will now show here. That's from a paper of Simon Thorpe. He's now retired. He was a theoretical, or is a theoretical neuroscientist at the Cerco Institute in Toulouse, CNRS researcher. So here we see a numerical, a computational spiking neural network. And what you can do is you let only a certain fraction of neurons spike. Yeah? So what you see here is if we only allow 0.1% of the neurons spike and we can reconstruct the information of the input using convolutional operations, then we already start to see some structure of the input image. If we now increase this to 0.2%, it's almost completely identifiable as, you will see, a bridge. Yeah? And this shows that you can use spiking neurons for very, very aggressive information compression. What this scheme uses and information encoding is not the spike rate, but it uses the delay between input stimulus and the neuron spiking time. And this is called spike latency encoding. And as you can see here, for different images, neurons correspond, because the image is always injected at this kind of step here, neurons respond to a very different delay. Now we can implement a very efficient scheme. We can say, okay, we inject our information and now we wait a certain number of time steps, and only in this window we allow neurons to spike. After that window, we switch off the power supply, and this allows us to save a lot of energy. Importantly, this is only one global control variable. Again, we don't care at all about what the individual neurons do. We only control the length of the time window after a stimulus for which we allow neurons to respond to that stimulus. And here, for example, this is what happens if we only allow one window, one integer time step here, then only 1.02% of all neurons are spiking. If we allow all of them, then on average 81% of the neurons are spiking. And this is controlled, this ratio is controlled by a single parameter. So we've implemented this system and we have now trained, again, the output weights of that system using another algorithm, which is called SPSA. I will not go much into detail here. It does not work on a large population of these different configurations of the weights, i.e. our SLMs. It only repeats these measurements twice. Once for a random negative perturbation on the weights, and once for the same random but positive perturbation of the weight. And with this, you get a stochastic approximation of the gradient, and then you simply do gradient descent on the weights. So that's a very low complexity training algorithm, and hence the name simultaneous perturbation stochastic approximation. So we use that to train the spiking system. And the fascinating results you can now see here is we plot sparsity as the x-axis, and we plot performance for training and testing on the y-axis. So you can see here that the performance in robustness is, the performance versus sparsity is very robust. It actually, sparsity is beneficial, and that's backed up by theory. That means the least, or the less neurons we allow to spike, the better the neural network gets. And this is because patterns become more exclusive. It's harder to find a pattern where only 5% of the cells are supposed to be active than when 50% of the cells are supposed to be active. So that's more or less the hand-wavy argument behind this. So besides this, what we can also see is that the drop here is actually quite forgiving. So that means we can go until 90% sparsity and still achieve close to 80% accuracy for solving this symbol recognition task. We can go even further. We go to close to 2% sparsity and we are still at 60% accuracy. And this is now very important because you can tune the properties of your system with a single global variable. For example, flight or fight responses. For example, if a robot needs to react very quickly to a critical situation, i.e., I fall down the stairs, then you want to be very quick and very efficient. So you make this reply very short-lived only. But if the robot should, for example, contemplate, should I do this rather complicated action, then you give it a little bit more time to basically reflect upon this decision. And you can do this nice tuning now between efficiency and speed of response with a single kind of tuning knob. So this is for me where one of the big powers of spiking systems work. Okay, now to wrap this up, I'm coming to the cost of training an analog system.
You have 3 minutes, Daniel. As you
Good, perfect. So there's two approaches right now in the field. We can use this approach called physics-aware training in a great paper by Logan Wright, Peter McMahon, et al. In 2022 in Nature. And they create a digital twin, which they train or optimize in order to mimic the physical system. And then they pass the data through the physical system, but also through the digital twin, replicating the dynamics of the physical system. But when they want to update their weights, they only use the now differentiable digital twin in the backward direction. And with this, you can essentially force the error backprop mechanism to be implemented in a physical system. And what we are doing is we are trying to optimize the black box and we are treating it as such. So, and here I can only show you so far our analysis of this cost using black box optimization in a collaboration now together with Peter. We are also extending this to their physical twin model. And this is not yet published results. What I want to show you here is that first of all, number of parameters versus accuracy. I showed you before. It also then depends a lot on the training algorithm. This is again for our lasers. SPSA, this vary only 2 iterations per epoch versus different kind of black box population-based algorithms. So now what we did is for different sizes of this neural network, we measured how much memory do we actually consume in order to train our system. And we plotted this as a number of parameters. And you can clearly see that there is this orders of magnitude scaling difference between them as memory budget for best accuracy, i.e. to convergent in gigabyte. So first you can see that this makes a large difference, but this does not tell the full story because it does not link it to accuracy. So linking it to accuracy you can see in this plot. So to train our laser neural network using SPSA, we can actually go to almost below a megabyte for the smallest neural networks. So it's very, very, very efficient. However, if we go bigger, we need a couple of tens, 100 megabyte maybe, but performance remains very mediocre. And now we have 2 different of these population-based algorithms to compare, and we can clearly see both of them reach the same performance, and the one we actually thought would perform best in terms of accuracy is this one. However, you can see we go from essentially gigabyte costs of training it to terabyte costs. So there you see this gigantic interaction in terms of, first of all, benefit of training the full system, because in performance, because SPSA cannot leverage the input weights or the internal weights, it's just too crude for that, but also the charge you place on your algorithm and on your hardware outside of this. And this places a little bit at jeopardy this entire concept of building efficient neural networks if we do not solve the problem of training them efficiently as well. Good. So some final thoughts. I do not need to talk about integration. I think that's clear. I skip that. The final thought I want to communicate here is what is done a lot in the field is we create very small model systems And then we extrapolate, because we need neural networks comprising thousands or millions of elements, and we just extrapolate a linear scaling, let's say, between those. The reality, unfortunately, many times is different. It is like this. And this is actually very powerfully demonstrated by this breakthrough paper in Nature Photonics 2018, I think, where they calculated, and then the startup coming out of this, they created this really absolutely amazing hardware. It's a PCI system. You can program it with Python, and you can implement a large language model on this system. So I admire this work. I'm not trying to disqualify this work, but they come to the same conclusion. Funny little detail is someone screwed up the PCB design. So here you can see a hand-soldered wire. But what the extrapolation of their original paper was 10 to the minus 6 picojoule per floating point operation. Where they end up with is 1.2 picojoule. And that's exactly the same as the NVIDIA system. And I do not have time to show the scaling arguments leading to this. The problem is these scaling arguments are the worst for the time delay multiplexing, because then you need actually this external memory for every little way to implement. So that's basically the summary of this. And if you're interested in kind of a real world contrastion of how difficult it is to beat NVIDIA at the game or digital computers at the game, I recommend to you this article by a pioneer of optical computing. I think it's from 2012 or 2015, where he already says, 30 years ago, this was what I knew for a fact. Electronics reaches natural limits. Optics alone can offer massive parallelism. I was all wrong, because computing is much more difficult, as you can see in this image. The actual optical unit is very small. The rest around it is scheduling, trying to make it reproducible, trying to control it, interfacing, etc., etc. And this is where the energy is burned. Unfortunately, not here. This will only start to save energy if we make the optical analog in-memory computing unit much, much bigger. And with this, I really thank you for your attention. And it was an honor for me to present our results and what we have done in the past. And I'm happy to take any of your questions.
Thank you very much, Daniel, for this brilliant presentation. Now, do the audience have any questions? Ariel, if you have one question, can.
Good or clear?
Yes, I have difficulties to have the. Yeah. Okay. Do you hear me?
Yep.
Okay. So no, it's a simple question. Try to link the paper and your previous work on reservoir computing to what you said in the first part. If I well understood, I had to check if I well understood. Is there any limitation, a fundamental limitation that gives this 90% efficiency without training, and or can you shape as proposed by Daniel the reservoir for a given task to go further to do better without training?
Yeah, it's a very good question. I think to answer this question is first you use the word defining this 90% threshold limit. And I think the word defining here is motivated by us being physicists. We try to look for the fundamental law of nature saying this is the limit. The problem is that the tasks we use for neural networks, they basically by their nature do not have this limit because they're very abstract and complex. So I cannot give you an analytical equation saying this will be the limit. But what we can do, of course, we can do a scaling analysis. We make a reservoir bigger and bigger, and we make a fully trained system bigger and bigger, and we compare their performance. And what happens there is something which is very interesting until you reach, let's say, 93, 94%, 95% even. With the reservoir, you can get pretty good, pretty close to the fully trained system. But as soon as you try to surpass a certain performance, the size of reservoir you need starts to exponentially explode. meaning you reach the expressivity or the useful expressivity limit of the reservoir. And if you then have a system that you can train, this explosion in size is much more gentle. So at this point of where the resources a reservoir needs is exploding, you can calculate the ratio between a trained neural network versus a reservoir for this kind of performance. And it turns out that you need a reservoir that's around 50 times larger than a normally trained neural network.
Okay.
So that can be absolutely acceptable. For example, if you can make a computing at a picosecond that a technology or a new experimental scheme requires to be done, then this is justifiable. But you will not beat a computation for which you are not so resource constrained using a reservoir. You will always have the better system then where you can train everything. But this is more or less the limit. The problem is that this limit shifts depending on the task. If you, for example, want to do a large language model kind of computation using a reservoir, you can stop directly at the first word, I guess. It's simply not happening. So this is the problem. There is no real analytically derivable limit for these kind of things.
Very clear. Okay, thanks. If there is no other question, I have a little one.
Yes, please, Ariel.
Yeah, yes. When you discuss the number of the neurons, still on the first part of your talk, the number of the neurons, you never mention any property of the physical system. I mean, is there any optimization? If you think about the Nolian bullets, you can think about between nonlinearity direction and other things of the system that the size of the individual bullet. Here, you didn't mention any.
Yeah, so this is for a VCSEL with around 50 micrometer aperture size diameter. And besides this, we have not optimized anything yet. So what we see, and this is why this next plot is so important, until now, we were not really sure where the physical origin of these dimensions come. Because the modes of the laser, they are distributed, they're not all at the same time. They have different lasing amplitudes, different thresholds, therefore also different nonlinear terms. So it's a very black box system per se. And we're only trying to peel off now the different correlations, understanding what happens. And it appears that the first importance is when we inject our system here at 977.5 nanometer from the external laser, what we need in order to get the largest neural network within the same laser is that most of its modes are very close to in vicinity of this. And this is, in my understanding, due to the injection locking bandwidth of this particular system. But we are at a really early stage where we start linking this now to the physical properties of the system. Our colleagues in Poland, they have a very complex numerical model, and they will then basically try to find out what are the interactions behind all of this. So I hope in a year or two we have the answer for your question, but it's exactly the research direction I'm trying to take right now.
Well, I'm a PhD student onto optical feedback sensing. And so I have some knowledge about the difficulties and the models behind the transverse mode dynamics with optical feedback. And you responded to my question with the end. It was like if you had some kind of simulation, you are into the process of optimizing the VCSEL for your neural networks. And you pretty much responded to my question. It was like it was just, do you already try to see if the transverse mode dynamics have an importance on your dimensionality of your neural networks?
So This data is from 2 days ago.
Okay.
So,
Then
it is
it is
so.
very impressive, yes.
So we have some earlier data indicating this. We're really getting into this dynamics right now. Your question
Okay.
is really interesting because it illustrates the importance for something. The numerical models for large VCSEL lasers are numerically essentially untractable. For simulating only the switch-on dynamics for such a large device for a couple of, let's say, 10 nanoseconds, we need days of a cluster. So that means it is impossible that we can use neural network simulations to measure its performance because it would take years on a cluster to get to a curve like this. So this is why we have these two logical steps. First, we try to derive a dimensionality measure approximation of our system without training it in a neural network task, which is the principal component analysis, because that we can do within within 1 minute for one laser for one parameter. Then we can train it. That already takes an hour or two. And with this, we validate this very, very quickly attainable characteristic as an important measure of computing. And then we try to now link this to steady state properties of the laser itself, which we can then link to, let's say, steady state solutions of the model. If we would have to calculate the dynamical response to optical injection of this model, it would absolutely be untractable, and we would never get towards optimizing these devices. So this is why this kind of chain of argument is so important, because this is a general fact about high-dimensional nonlinear dynamical systems. They are very painful to optimize, but data-driven computing as AI requires thousands and millions of examples until we know the computing performance. So we need to find different ways of basically gauging their application. And for example, with a PhD student previously, now postdoc in my team, Mathilde Harry, and a group in Tampere, we extended this also to nonlinear fiber propagation so basically a nonlinear Schrödinger equation systems, and John Dudley has published now numerical work around this. So this shows why is it so important to not only compute, let's say, MNIST calculation, etc., but to link this to the underlying matrix of the system that we can then link to the physical system properties, because otherwise we will never get towards really understanding the interactions.
Okay. Thank you so much for the presentation. It was very clear.
Thank you.
Okay, thank you one more time, Daniel. So
It was
if
my
we have
pleasure.
no
Thank you.
more question, we can move to the next presentation. Fabrice, if you can share your screen.
Going to try to.
So let me present you Fabrice. Fabrice RAINERI has been professor since 2021 in the physics department at Université Côte-d'Azur, conducting his research at Institut de Physique de Nice. He is also one of the co-founders and the chief scientific officer of NcodiN. His academic journey includes receiving his PhD from Université Paris-Saclay and serving as a postdoc at ICFO. He then spent 16 years as an associate professor at Université Paris-Saclay, conducting his research at the Center de Nanosciences et de Nanotechnologie, C2N. His current research interests are focused on the investigation of optical nonlinear interaction within semiconductor micro nanostructure and their exploitation for the achievement of optical functionalities using for data processing. Recently, he led his work towards integrated nanophotonics with a specific effort on hybrid 3-5 semiconductors on silicon structures. He has participated and worked on numerous national and European projects. He was awarded with an ERC Consolidator grant in 2017 and ERC Proven Concept in 2022. He was nominated as a finalist for Prix Jean-Jacques Fagnon in 2022 and as a senior member in 2024 of Institut Universitaire de France. He has published more than 100 articles in peer-reviewed journals, filed 6 patents, and participated to many conferences. So please, Fabrice, you have now the floor to give us an overview of the situation from the industry's perspective.
Thank you, Yannick. Can you hear me? It's okay and see my slide?
Okay for us.
Okay, thank you very much. So it's a pleasure to give this presentation, and I try to set up this slide about what's the situation in the industry when we mix the words photonics and artificial intelligence. And so if you just type on Google these two keywords, you can see that many companies will pop up actually, and like maybe like every month there are some new companies will appear trying to exploit photonics for AI. And but still you have some of them which are now quite large, such like these American companies, such like Light Matter, IR Labs, Celestial AI, Light Intelligence. And so for the US, for example, and of course in Europe, you have also very nice activities in Germany with the Black Semiconductors and Photonics, for example. And in France, we have some companies working in this domain. And what is very interesting right now, you can see also that extremely large companies are also focusing some work on using photonics to enhance their AI system. And of course, if you are working in a startup company, what you want is to collaborate with very large companies such as Broadcom, Intel, and especially NVIDIA, which is the leader of AI in the world, with more than 90% of the market for the installation of data centers dedicated to AI. So yeah, so if you look at, of course, this triggers a lot of investment in this company, especially in the US, with billions of dollars spent in there. So why photonics? So we had two beautiful talks given by the previous speakers, and of course, why photonics for AI? So, and most of you are in this domain. And what Daniel showed, of course, first things is, of course, photonics is extremely interesting because it handles data transmission like no other technology. If you want to transmit data over a certain distance, I mean, the best way is to use photons to do it. And why? It's just because light interacts poorly with matter, and you can propagate information without loss almost for a very long distance. And light propagates very fast, of course. So when you have some application which deals with problems related to latency, reach, bandwidth, of course, photonics will be interesting. And also, what photonics promises, of course, is to reduce the power consumptions of all of this system, and of course, ultra high speed technology. Even though, as Daniel said, there is some strong competition with respect to electronics. And if you look at the goals, what targets all of these companies, you can see there are two types of companies, and some of them that flipped their focus during the years. First of all, the immense majority of this company focus their works in photonics to enhance electronic systems. It is the case, what they want to do is to provide optical interconnections for electronic systems. So many of these companies focus on optical interconnects. And now few of them also, because of the progress of research, of course, they try to replace partly electronics somewhere in order to provide optical computing functionality. So what I have to say there is that many of the big startups, such as Light Matter, Light Intelligence, Celestial AI, all of these companies pivoted from the second one to the first one in the latest years. So during my talk, So I will follow this clear distinction, how photonics can help for AI with optical interconnect technologies and what people are doing with that. And also, what about optical computing? So let's go with the optical interconnect technologies. So yeah, so there will be no surprise there. If you look at a data center dedicated for AI, what it looks like, especially for the very large training systems for ChatGPT, for example, these data centers are huge, complex, containing more than 100,000 servers, which contains themselves 8 GPUs made by NVIDIA most of the time. And in these hyperscale data centers, of course, they are used for these large training models where they train billions of variables for their models. And if you look at now the interconnections operating in these data centers, if you count the links, there are millions of links interconnecting all of these servers together in order to provide the sufficient power to address this training of billions of variables. And all of this, of course, triggers humongous power consumption of about 10 to the 5 megawatt per hour, megawatt hour, which is approximately, imagine 10 times the power consumption of a city such as New York City, such as New York. So this is very scary, and of course the forecast for the future is are terrible for power consumption linked to ICT, for information and communication technologies. Daniel talked about 20% of power dedicated to this technology by 2040. So this paper was a bit older; it was 2030 in here. And of course, for us, it triggers a lot of motivation to introduce novel technologies for this data center, because not only we want so they have to work, but this industry wants to scale up, of course, the capacity of these data centers in the future, and so we have to do it in a sustainable manner. And of course, photonics has to play, will play a major role in this domain. So photonics, as you know, is the best way to transmit information across networks. And of course, it helps to reduce the power consumptions in these data centers, because a lot of power is consumed for communication in these electronic systems. And due to Joule effects, not only it consumes power, but also it heats up the building, and you have to cool down this building. So it's terrible. So we know that photonics has started to replace electrical connections for many years. First by replacing very long distance communication systems, and now everybody has fiber to the home, at least in France. And yeah, in the 2010s. So in order to address the problems of interconnect in data centers, so there are like a huge market for pluggable transceivers with optical cables to transmit data from servers to servers. For example, there's this huge market where photonics is there. And now the attention, of course, is directed towards shorter distance communication links, shorter and shorter. So right now, many of the companies that I showed in the beginning of my presentation addresses the problem of what's called co-packaged optics transceiver, where now it's not the servers that you are going to interconnect together, but you're going to interconnect processors or GPUs systems together, thanks to a packaging very close to electronics and even on electronics. So the idea is you will be able to interface this processor with optical fibers that are plugged directly with the electronics in order to enhance the capacity of these huge electronic systems. And the next frontier, of course, is not only to introduce links between what's called system in package, but also inside itself, these new processor systems, this system in package, in order to provide what's called die-to-die connectivity and address centimeter range communications inside the chip itself. So photonics will be in the future everywhere. This is what I believe for communication. And let me now show you a little bit of what's going on for first co-packaged optic transceivers. So this is what it looks like. As I told you, there's a chip system in package where the chips is made. And on the border of this processor, you will have some input and outputs that will be optically connected directly with optical fibers. So this time, it means that photonics and electronics are integrated together in the same package. So this is addressed by very, very large now startup companies, and we can cite also Scintille Photonics in France. And of course, NVIDIA is leading the way in there with some new products that has just been out now. And why people want to do this, of course, is to accelerate training and inference processes for AI models by enabling this faster communication between processors and diminish also the power consumption of all of this system. So why now this technology? Of course, it's a market pool need. It's a market pool products. They are market pool because it is needed. But of course, this was prepared. It has been prepared for 20 years now with all the development on silicon photonics. And the silicon photonics for this technology is a true game changer. Why? Because it allows the fabrication of these photonic devices into CMOS fab where electronics is made. And so why it is so important? Okay, it's not only because investment is already there, but it is important because the standard of fabrication are so high that they reach some reproducibility inside the chip and from wafer to wafer, which is extraordinary, and which will change forever, I believe, how photonics is made in terms of course, reproducibility and also reliability. And if you look at these technologies, so they are based on optical links. And to make an optical link, what you need, of course, is some functionality which allows conversion from electronics to optics, and also back from optics to electronics. And these are three important devices, components that are forming these circuits. So first of all, many of these approach for these interconnects are based on the use of electro-optical modulators, which convert electrical signal into the optical domain. And what is used, the most common way to do it now with silicon photonics is to use what is called a carrier depletion modulator. So this is here, for example, an example with a ring resonator. where basically you input some light into the waveguide, which is coupled to the resonator, and you change the refractive index of the silicon by applying a voltage onto this diode in order to change the transmission of this system. So this is a common way. You can use other types of configuration, such as Mach-Zehnder interferometers, of course. So the other important device is a photodetector. And now, what is accessible in the CMOS is these germanium on silicon photodetectors, which are efficient and very fast. And also, what you need a source. So here, I put an example of a hybrid laser, which is made onto silicon, but most of the approach for these co-packaged optics is based on the use of an external laser to the silicon chip. So what is very nice with the progress of technology, thanks to years of research in the academia, these devices work quite well, and they can provide ultra-fast electro-optical and optoelectronic conversion well beyond 40 gigahertz, which is needed for these co-packaged optic systems. And yes, if you look at some products linked to this co-packaged optics, so you can find some products offered by IR Labs, for example, which promise 1,000 times bandwidth density enhancement for the tenths of the power compared to electrical I/O. And of course, NVIDIA. And if you look at all of these products, they are based on the use of external lasers plugged in a silicon photonics chip, which contains modulators and photodetectors. And now I'm going to play this video from the latest product by NVIDIA on co-packaged optics, which is, as you will see, very impressive in terms of integration for photonic component. It's very, very impressive. Sorry for the sound. So you will see inside these co-packaged optics-based systems where they have silicon on insulator chips, which contains, as they say, which is able to go to 28 terabyte throughputs with 36 lasers. Okay, I let you read. It's simpler. So what is nice is to see how all of this is packaged with optical fibers. What they say, they have 1,000 single mode fibers out of the system, which is absolutely amazing, which couples lights into the system, but also couple their system to the external world. And this is extremely exciting to see as a company such as NVIDIA, a global company that sells photonics like this. I think it's really important. Okay, so sorry, okay, so now let's move to another aspect of optical interconnect, which is this die-to-die connectivity. And now we are moving from interfacing elements which are placed meters away to now systems that are placing on the same chip centimeters away to each other. So this is what the industry is doing now for these advanced processors. Now a processor is not only, or GPU systems are not only made of a single package, like a single chip, but the industry has pivoted to disaggregated chiplet-based solutions where they interface a little chip, what's called chiplets, together onto a host substrate, which contains the communication lanes to make them work all together. So basically, for example, this NVIDIA H100, which is one of the most known GPU system, interfaces the GPU with this high bandwidth memory on the side onto a single package. And of course, what people want to do is to increase this number of chiplets on the chip. And if you see, you cannot increase the size of this chip too much, because now the cost of increasing the size of these chips is not sustainable for the industry. So this is what chiplets are used. So if you look at what NVIDIA wants, for example, they want to go for these very most simple structures. To now they have this Blackwell system which interfaces two GPUs with a CPU and 8 HBM. And this year, Jensen Huang presented the dream of NVIDIA is to have these very large chips, like a full data center onto a single wafer, basically. And of course, with the current technology, with the electronics, it's not possible because the bandwidth density is too small and the reach is not enough with electronics, and the power consumption is too big. And of course, what we want to do in photonics is to break what's called this copper wall, which prevent these systems to scale up. And as you see, as you want to increase the number of these chiplets beyond 10, then you start to this performance start to saturate. So and with photonics, of course, we want to allow this scaling of super chip performance. And so I'm going to talk a little bit of NcodiN now. So the company I co-founded. So what we want is to, of course, make an optical permer. Sorry, the slides are not so good. Which is powered by the world's smallest lasers made on silicon. So basically, the chiplet will be interfaced on top of an optical interposer, which contains optical links, and also some optoelectronics converters, which converts electronics to the optical domain and optics to the electrical domain. And basically how it works, basically, is you will have the chiplets are packaged with little bumps under them. And what you will do is to stick directly these bumps onto the lasers and photodetectors in order to provide links at the millimeter scale, centimeter scale that is needed on the chip. So to be fast now on, let's move to optical computing. So Daniel talked beautifully on why light wants to be, why we want to use light to compute. Of course, most of us come from nonlinear optics, so we are so very excited in doing some calculations with light. But if you look how it works and what people are doing right now. So you have some people who are focusing their work on doing matrix vector product with using linear optics, which is of course much simpler to do than electronics. And for example, some people use fashion material to set the right weight for the network. And so this is for me, very important breakthrough for photonics as well for AI. But in the end, what we would want, of course, is to have maybe an all optical system which is also able to provide the nonlinearity necessary to compute data directly in the optical domain. And so now, so of course, there are lots of work done in the academia because it's a very exciting domain, and of course, this technology can bring a lot on this. And again, the previous speakers showed impressive work on that. But now, if you look at the companies, so the very few companies actually now really aims at doing selling some systems with neuromorphic all optical computing. It's because, of course, because you have to compete with the electronics. And here, just to talk an example of product, so Daniel showed something that Light Matter did years ago. I don't know if it is still a product for them. But so Light Intelligence, which is another American company, sells what they call PACE, this photonic arithmetic computing engine, which is again an optical circuit which is doing optical matrix multiplication with a silicon chip. And it's really about kind of manipulating data in the optical domain to provide this functionality of matrix multiplication. However, it is not, of course, an all optical neural network because the nonlinearity and the decision then is coded in the electronics, of course. So nonlinear photonics. Okay, so now there's no product on the market which is used directly nonlinear photonics for accelerating AI. So in conclusion, so I guess we are all convinced that photonics truly brings about a revolution for this ICT and for AI, and enhancing AI with photonics, AI electronic system with photonics is really a killer application, triggering enormous activities in the domain because photonics brings unmatched performance for interconnections. And this is all enabled by breakthrough of silicon photonics. And right now, co-packaged optics and interposers are key products which are on all roadmaps of giants of microelectronics. Of course, all of this solution needs a huge investment for industrialization because this is now it strikes a nerve. It's very important to produce reliable devices in photonics. And so, yeah, the question is, so what about all optical data processing? Is it truly a good way to think that we are going to replace electronics in some part with photonics? So for me, I think we have to see it either as a complementary approach, or of course are there applications for all optical computing not in competition with electronics, for example like in optical networks. And to the last word, I would say that this, I mean, for example, with the video I showed you on NVIDIA, we can truly understand that there are exciting avenues that opened up and that are open in front of this domain. And it is just the beginning with this introduction with the electronics. So with that, I would like to thank you for your attention.
Thank you very much, Fabrice, for this very enlightening and informative presentation. So now the session is open for question. Do you have a question? So maybe I can start. You didn't give a lot of details on your laser. So what are the size, and do you still working on the miniaturization, or is it enough for the moment for the industrial point of view?
So thank you. So the lasers, so the optical mode is like few microns long, okay, and the total laser is contained into a surface of 100 micrometer square on the chip. So this is already very aggressive compared to other types of lasers. And if you look at the need, so these systems, the optical systems, have to pay what is called universal chiplet interconnect standards, so UCIe. And in these standards, they have some, of course, some requirements in terms of bandwidth. Okay, it's not such high bandwidth. Basically, between 10 and 10 gigabit per second is really quite okay for all of the system. And on the size, so it depends on the pitch of the bumps of on this system. So now, for example, the pitch is of about 40 microns. So we are well below this limit in our case.
Okay. Ariel, if you...
Yes. Okay. Yes, very interesting talk, Fabrice, and I appreciate a lot the first part of the optical connects, because it gives me a very nice overview of what is ongoing in the industry. About the second part, what is your feeling? Is there you can already see or maybe detect a niche where the all optical computing could be suitable? I mean, maybe a little niche where, yes, a company should go.
Yeah, so of course, but first of all, if we have at some point, even in an electronic circuit, some optical signal that has been converted, that is on the chip, it would be good to have also some processing of this signal in the optical domain. So what I would see, for example, for maybe for all optical computing, maybe one of the applications, so I saw this in several European projects. One of the goals would be, for example, to be able to have an all-optical system which is able to handle attacks such as DDoS, denial of services attacks directly in the optical domain prior data centers. For example, if you would be able to recognize some pattern of an incoming signal into the optical domain, which looks like an attack, you would be able to switch the data directly to a bin without letting it go to the electronic system. So this, of course, for me, it would be a very nice way, and it would be also very important to have this type of systems which are able to treat data directly in the optical domain without going to electronics in order to switch the data. There are many also some other system which wants to compensate for dispersion and things like this.
But for this example that I didn't know, the point is that it should be local and fast. That's the point for going to photonics.
Yeah, exactly.
Okay.
The idea is to have like directly some data directly in the optical domain.
Okay, thanks. It's clear.
Philippe, you have a question or?
The micro. No, we don't hear you, Philippe. There is no micro open.
Okay, so if there is no more question, I would like to thank the three speakers. Thank you very much for these nice talks. And I think we will have, before the end of the year, the final sessions on this series. So I hope you will be all there for this last session. Okay.
Thank you, Yannick.
Thank you very much.
Thank you. Thank you all. Very, very nice.
Thank you.
Bye.
Bye.